Chapter 2, Lesson 4 of Pre-Calculus, looking at real zeros of the polynomial functions, and we're going to look at the rational zeros theorem in this lesson, and then we're going to combine that with what we learned earlier, the remainder and factor theorems and synthetic division, then to determine what the zeros are of a polynomial. So let's talk about rational zeros first of all to begin with. We know that real zeros can be either rational or irrational. What that means is if you think about the x-axis is actually a representation of all real numbers. That x-axis represents every possible real number that there is. And what we're looking for is any number on that x-axis where this polynomial will cross or touch. And we already talked about the only place it can cross or touch is at a zero of the function. So we would like to know where those occur. Well, we're looking at an infinite list of potential places that these polynomials could cross or touch because we're looking at anywhere along that real axis or that x-axis or those real numbers. Now all of those real numbers can be broken into a number of categories. You remember when we classified our sets of numbers, whole numbers, natural numbers, integers, rationals, irrationals, and reals. So that line actually represents all of the real numbers, so it represents the rational numbers and the irrational numbers as well. The irrational numbers, you remember, are square roots of non-perfect squares. So square roots of 3, square roots of 7, square roots of 11, those are all irrational numbers. Now, what the rational zeros theorem does for us is it allows us to make a list of the potential rational zeros of any polynomial as long as that polynomial has integer coefficients. So there's one exception here. When you're going to use the rational zeros theorem, the coefficients must be integers. So for example, if you had 1/2 x squared plus 3x plus 1, you could not use the rational zeros theorem because the coefficient of that first term was 1/2, not an integer. Now, we talked about this last year, and we did this last year, so hopefully you remember that in order to make your list, you take your factors of your constant, once it's in standard form, in the numerator, and your factors of your leading coefficient in the denominator, and then you write your list by putting each factor of the numerator over each factor of the denominator. So hopefully that kind of explains. I don't know if you should remember that, but let's do a couple of examples, and that might help jog your memory. So here we have a polynomial. It is in standard form, so I want to take my factors of my constant. So my constant here is 1. The only factor of 1 is 1. Over, and then I take the factors of my leading coefficient. The factors of 6 are 1, 2, 3, and 6. And again, factors are numbers that divide evenly into 6. So now we use these to make our list by taking each factor of the numerator and placing it over each factor in the denominator. So my list here would be plus or minus 1, that's 1 over 1, plus or minus 1/2, plus or minus 1 over 3, 1/3, and plus or minus 1/6. Alright, so there's my list. Now what does this list represent? Let's talk about that real quickly. What this list represents is this. If this polynomial has any zeros that are rational, okay, so if this polynomial function crosses or touches the x-axis at a rational number, it must be in this list. It will not cross or touch the x-axis at any other rational zero other than what's in this list. So what we've done is we've narrowed down our list by just looking at this and saying, wow, it could cross or touch on any real number. We've now narrowed it down to one of these, in this case, 8 numbers, 2, 4, 6, 8, plus or minus. Okay, these are the only places that it can cross at a rational number. Now, it doesn't mean that it can't cross at an irrational number. It just says if it's going to cross or touch at a rational number, it must be one of these rational numbers. All right, so that's what it does for us. It just gives us a list of potential rational zeros. Now, to determine which ones are zeros, we'll talk about that in a minute. Let's do a couple more examples. So here, our second example, we have a polynomial. It is in standard form, so we take the constant and we list the factors. Whoops, I already showed you that. Factors are 1, 3, and 9. And then I take the factors of my leading coefficient, which are 1 and 2, and now my list is made by taking each factor in the numerator, placing it over each factor in the denominator. So 1 over 1, 1 over 2, 3 over 1, 3 over 2, 9 over 1, and 9 over 2 to get my list. And again, it's plus or minus. So plus or minus 1, plus or minus 3 is 3 over 1, plus or minus 9, 9 over 1, plus or minus 1 over 2 or 1 half, plus or minus 3 over 2, 3 halves, plus or minus 9 halves. Now again, what does this list represent? If this polynomial has any zeros that are rational numbers, it has to come from this list. It will not cross or touch the x-axis at any other rational number other than the ones that are in this list. Alright, so let's do the last example here. So here it's in standard form. My constant is 12, so my factors of 12 are 1, 2, 3, 4, 6, and 12. All of those numbers divide evenly into 12. The factors of my leading constant or leading coefficient are 1, 2, 3, and 6. So this is going to be a fairly large list because I have to put 1 over 1, 1 over 2, 1 over 3, and 1 over 6, 2 over 1, 2 over 2, 2 over 3, 2 over 6, 3 over 1, 3 over 2, 3 over 3, 3 over 6, 4 over 1, 4 over 2, 4 over 3, 4 over 6, 3, 6 over 1, 6 over 2, 6 over 3, 6 over 6, and 12 over 1, 12 over 2, 12 over 3, and 12 over 6. Now, some of those end up being the same. They overlap with the same number. Once they reduced, you only need to reduce them or list them once. So when we do that, here's our list. So again, what this does now is it tells us that if this polynomial is going to cross or touch at an irrational number, that rational number has to be in this list. It cannot cross or touch anywhere else other than what's in this list. Okay, so that's the rational zeros theorem, making a list of potential zeros. That's how you do it. In the next video, we'll take a look at, okay, now that we have our list, how do we figure out which one of these is actually a zero?